the 20s, the Model A Ford was the sportsman's dream at 40 miles per hour, but times have changed. Wherever you turn, the way of living and the way of getting the job done drastically has changed. And speed, and more speed, is the order of the day. Even romance moves at a far different pace in today's world of bikinis and outboards. Tedious hand labor is largely replaced by mechanical devices that do the job better in a fraction of the time formerly required. Old manufacturing methods have given way to new. And the old-time blacksmith who toiled and sweated as he heated, formed, and punched raw steel into the needed part is almost forgotten in today's world of speed, ever-increasing speed, that challenges engineers, designers, manufacturing men, and maintenance men to find better ways to keep parts together. For more speed means more stress from vibration and impact, and more need than ever before for new and better fastening methods. In today's world of speed, vibration, and impact, old-time fastening methods are as outmoded as the log sled and hand forge. Manufacturers, therefore, have developed new types of locking fasteners to make today's equipment safe and reliable, and to keep it running. How the best of these locking fasteners stand up is demonstrated by this modified Junker machine, which applies severe shock and vibration. Elapsed time is measured across the top of the chart. A steel fixture plate is at the center. In the first test, a plain steel 3/8-16 grade 5 bolt is inserted and a nut run on from below. The technician sets the machine by moving the bar to the left. The technician then applies a predetermined load to the bolt. The tensile load is 5,000 pounds, which is 75% of the bolt's proof load. Next, he marks the head to show initial loosening. During the test, 2 air hammers hit the plate on each side within a predetermined range of impact and frequency. Initial loosening actually occurs before it can be detected on the chart. The technician starts the verification stopwatch, and the test is on. The bolt loosens in less than 5 seconds, and total loss of recommended proof load follows immediately. Next, the traditional lock washer is used with an identical bolt. The technician tightens the bolt to 5,000 pounds and marks the head. Initial loosening occurs in about 5 seconds, and the lock washer assembly quickly comes completely apart within 25 seconds. The plain bolt and lock washer simply do not stand up under modern vibration loads. Next is a bolt with a friction locking pellet. Loosening occurs before 10 seconds, with complete loss of preload after 35 seconds. The free spin type shows a slight preload loss which occurs when the teeth under its head embed in the test plate. However, the free spinner develops good locking ability when the head is clamped down tightly, retaining a high percentage of its preload even after 80 seconds, a big improvement over the plain bolt and lock washer. The free spinner, however, does not seal, and corrosion may occur on the bearing surface under the serrated head. Also new are bolts coated with microcapsules of anaerobic adhesive. When the nut is run onto the pre-coated bolt, The capsules crush, freeing the adhesive, which upon curing, locks and seals the assembly. Typical of this type of locking is Loctite Dry Lock. 5,000 pounds tension is applied and the test begins. Because the adhesive is pre-applied, time is saved on the production line. The bolt locked with dry lock retains after curing a greater percentage of its initial preload than any of the friction locking devices. The curve remains stable throughout the test, which is discontinued after 80 seconds. The dry lock joint not only effectively locks, but also seals against leakage and resists corrosion. The bolt locked with anaerobic liquid adhesive, here Loctite 242, retains the greatest percentage of initial preload. The marked bolt head shows no deviation from the black arrow. Chemically locked fasteners thus best meet today's punishing shock and vibration loads. The bolt head does not deviate from the original setting. The liquid anaerobic adhesive not only locks the bolt, but also seals the joint against leakage and resists corrosion. The following tests evaluate nut locking methods. The first test is on a standard phosphate and oil grade 5 plain nut and bolt. The technician runs on the nut, then tightens to give 5,000 pounds preload on the bolt. This is 75% of proof load per IFI specifications. Load is shown on the scale at left. The technician marks the starting position. Turns on the verification stopwatch and the test begins. The standard nut fails within 10 seconds. The technician next tests an ESNA stop nut, which has a nylon ring contained within the threads. He runs the nut onto the bolt, then tightens with a wrench to give 5,000 pounds preload on the bolt. He marks the bolt as before, then starts the watch. Even with dampening by the soft nylon material, the ESNA nut fails in about 13 seconds. The nylon ring provides continuous prevailing torque and never completely loses it, but very quickly loses preload. The nylon ring grips the thread planks in a spring action to increase friction. But nylon does not have a perfect memory, and prevailing torque decreases with each reuse. You need extra on-torque with ESNA nuts to overcome the friction between the nylon ring and the bolt threads. The larger the bolt diameter, the greater the on-torque. Another plain phosphate and oil nut is used in the last test. But this time, the technician applies Loctite 242, a lubricating and thread locking material which fully cures, even though oil is on the parts. The technician seats the nut to 75% of proof load and allows the assembly to cure at room temperature for 24 hours. Where desirable, you can use primer to shorten cure. He marks the bolt as before and starts the watch. Vibration does not loosen the assembly. The white mark on the bolt shows no deviation from the arrow. And the test continues without bolt loosening for 80 seconds, at which point the test is discontinued. As shown in these tests and the previous tests on bolts, chemical locking provides the most reliable assembly method. Modern-day cars, trucks, conveyors, and other high-performance equipment will continue to pose problems of fastener reliability and safety as speeds and loads increase. Designers, production engineers, and maintenance men can largely solve these problems, however, by turning from traditional fasteners to newer and better methods. Chemical locking, for example, as we have seen, resists shock and vibration better than mechanical fasteners, and in addition, seals against leakage, resists corrosion, and is suitable for high-speed production. All vitally important in keeping pace in today's changing fastener world.